In example 2, we have that a researcher wants to know if the mean TRZ level in the blood is greater than 14.2 in cats. 5 cats have their TRZ levels tested, and the results are as follows. So we have 5 different numbers here representing the TRZ levels in 5 different cats. At the 1% significance level, test the researcher's claim. So we are given, the researcher wants to know if the mean TRZ level in the blood is greater than 14.2. And so we are going to take our mu to be equal to 14.2 because that's what the researcher is going to be comparing it to. They tell us that 5 cats were tested, so that gives us our sample size, our little n is equal to 5. What we are not given is the population standard deviation. We do not have sigma. And also we cannot find sigma because we do not have population data. So unless we're explicitly given sigma, we're not going to be able to find it. So instead of using the population standard deviation, we will be able to take this sample of numbers from these 5 numbers and compute their standard deviation to give us little s, which is the sample standard deviation. From that sample, we can also calculate the sample average, the sample mean, our x bar, because that also was not given to us. They did give us that alpha is equal to 1%. Be careful when converting that to a decimal. That is 0.01, not 0.1, which implies that our level of confidence, which is 1 minus alpha, will be 0.99. So we will be 99% confident in our conclusion. So now I'm going to pull up my calculator so we can compute the sample standard deviation and the sample mean for this set of data. So now that I have my calculator pulled up, I'm going to hit stat, S-T-A-T. I'm going to hit stat, and then I'm going to hit edit. So I'm hitting enter on edit, and I will enter in this sample data that we are given. So we have 15.6, 13.2, 14.7, 14.9, and 13.9. Now that I have my data entered into my list 1, I'm going to hit stat again, and this time I'm going to move right over to calc, and I'm going to hit enter on one variable stats. I want to calculate the one variable statistics for this data set. It gives me list 1, which is where I entered in my data. So now I'm going to go down and hit enter on calculate, and it gives me several statistics, and the 2 in particular that we are interested in are the sample mean of 14.46, that x bar is equal to 14.46, so I will go ahead and put that down here. And the second thing that we need is our sample standard deviation. So be careful here. Make sure you are choosing S sub x instead of sigma sub x. Sigma is the population. This is not population data, and so we're not going to be using that. So we are going to be using the S. So I'm going to round that to about 4 or 5 decimal places just to avoid a rounding error. So our S is equal to 0.92898, rounding that to 5 decimal places. So now we have the information that we need to begin our 5 steps. And keep in mind that this time we will be using the t-distribution because we do not have sigma. We do not have the population standard deviation. And so we will be using the t-distribution table. So for step 1, our null hypothesis always gets the equal. It is that mu is equal to 14.2. That is our HO. Our HA, our alternative hypothesis, in this case will be that mu is greater than 14.2 because the researchers want to know if the TRZ level in the blood is greater than 14.2. So HA is that mu is greater than 14.2. So we automatically know that this is a right tail test because the inequality in the alternative hypothesis is pointing to the right. For step 2, we will now calculate our test statistic using the formula that t is equal to x bar minus mu divided by s divided by the square root of n. So this formula has the s in it now instead of the sigma. Our x bar we got from the calculator of 14.46. Mu was given to us in the problem of 14.2. Sample standard deviation we pulled from the calculator and we rounded that to 0.92898. And the sample size we were given in the problem is 5. I will round this test statistic to 2 decimal places to get 0.63. So now that we have our test statistic, we are ready to move on to step 3, where we determine our critical value and draw our rejection region. So I'm going to sketch a bell curve. And in this bell curve, I'm going to put the entire alpha, which is 0.01, on the right, because this is a right tail test. So we have an area of 0.01 on the right. I am shading that region. That is our rejection region. So we have 0.99 area on the left. We are using the t-distribution table. And so I'm going to head over to my t-distribution table. Our degrees of freedom is equal to n minus 1. N in this case is 5. And so our degrees of freedom is 4. And this is a right tail test. So now heading over to our statistics table and scrolling down until we get to the t-distribution table. So now that we are looking at the t-distribution table, we have one tail. I'm looking at the one tail row, and in that one tail, our area there is 0.01. Be careful not to confuse that with 0.1. Our one tail area is 0.01. And then we're going to go down to our degrees of freedom, which is 4. And so that tells us that our critical value is 3.747. 3.747. So we have 3.747 for our critical value. And now we will take our test statistic of 0.63 and drop that into this picture. 0.63 is rather close to 0, so that's going to be closer to the middle of this bell curve. And we see that this does not land into the rejection region. So our decision in step 4 is to fail to reject the null hypothesis. And we make that decision because the test statistic does not land in the rejection region. And so because it does not land in the rejection region, we fail to reject HO. And so since we are not rejecting HO, I'm not going to cross HO out. We are in fact rejecting HA. So we need that information to move on to step 5. In step 4, we made the decision to fail to reject the null hypothesis. So we are actually rejecting the alternative hypothesis. We need that information to write our conclusion. I always start off with the significance level when writing my conclusion for a hypothesis test. So at the 1% significance level, that is the alpha that was given to us in the beginning of the problem. At that significance level, there is not enough evidence to support HA because we are rejecting HA. So there's not enough evidence to support that the population mean, because we are doing a hypothesis test for a population mean, TRZ level in cats is greater than 14.2.